Hi everybody, in this video we will do 3 free response questions that I created for this unit. So let's get started. So 15.00 grams of hydrogen fluoride and 23.93 grams of barium hydroxide are dissolved in water, and the following reaction above occurs. If all the fluoride in the resulting reaction is precipitated as calcium fluoride, how many grams of calcium fluoride are expected to be produced? Now, when I read this problem, I see that it involves limiting reactants, and I see that it involves multiple reactions. And to get things started, I know that I have to deal with moles eventually, so I want to compile a list of the molar masses of each of these substances so that I can calculate the moles of each substance. So the substances that I want to calculate the molar masses for are hydrogen fluoride, which turns into hydrofluoric acid when dissolved in water, barium hydroxide, and calcium fluoride. I probably want to find the molar masses of those, and maybe even the fluoride as well. So let's write the formulas for each of those. Hydrogen fluoride is HF. Well, actually, let me write this on the bottom. HF. Barium hydroxide is BaOH2. And calcium fluoride is calcium fluoride with CaF2. Now let's find the molar masses for each of these. And I'll use a periodic table in order to do that. So here I calculated the molar masses for each of these. And now let's think about what the problem is asking for. So it's saying that the hydrogen fluoride and barium hydroxide will react, and the reaction above will occur. So this is a net ionic reaction between hydrogen fluoride in the aqueous form, also known as hydrofluoric acid, and combined with OH-, which comes from BaOH2 dissociating into one BH and two OHs. So we can go ahead and write that reaction. Barium hydroxide, aqueous, and let me put a 2 there, will dissociate into barium 2 plus aqueous, and 2 OH minuses, aqueous. So with that in mind, let's keep on reading. So it's going to react, so the OH here and the HF here will react to form some fluoride anions. And these fluoride anions are precipitated as calcium fluoride. Now, what does that mean? Well, it means that the fluoride will precipitate with some calcium ions in order to form calcium fluoride. So we have to add calcium ions. And in order to balance this, we need to put a 2 here because calcium fluoride has 2 fluorides and 1 calcium. So this is what's happening. And now let's figure out some things. Let's figure out how many moles of hydrogen fluoride and how many moles of barium hydroxide there are. So I'll do that on a new page. So here I calculated the moles of hydrogen fluoride or hydrofluoric acid in the aqueous form, as well as the moles of barium hydroxide that are dissolved. But the reaction is not between this and this. It's between hydrogen fluoride and hydroxide. So we have to single out the hydroxide from this. So for every 1 mole of barium hydroxide, there are 2 moles of hydroxide in it. So we can do conversion factor based on this reaction over here. Oh no, not that one. This one, which claims that for every 1 mole of barium hydroxide, we produce 2 moles of hydroxide. And that makes sense. So for every 1 mole of barium hydroxide, so I'll write barium hydroxide out, we have 2 moles of, well, hydroxide. And let's now convert this. So if we want to have moles of OH minus, we take 0.13966 times 2 moles of OH minus per 1 mole of barium hydroxide. and I forgot to put it here, but that should have barium hydroxide as well, and its moles. So notice how the moles of barium hydroxide cancel out because of unit canceling, and we get twice as many moles of hydroxide, or about 0.2793 moles of hydroxide. Now that we have the moles of hydroxide and moles of HF, we can look at this reaction and determine how many moles of fluoride are produced. So we see that the reaction is in a 1-to-1 ratio. So let's figure out which one produces more product. So let me move on to another slide. So now after erasing everything, we can figure out how much fluoride each reactant produces. So HF and F- are in a 1-to-1 ratio. So for every 1 mole of hydrofluoric acid that reacts, 1 mole of fluoride will be produced. So I can safely conclude that for every 0.7496 moles of HF there will be the same amount of F-, or 0.7496 moles of F-, because they're in a 1-to-1 ratio. And same goes for here. The ratio between OH- and F- are also in a 1-to-1 ratio. So we can safely conclude that OH- can produce 0.2793 moles of F-. Now we see that the OH- produces less product, so thus this will be the limiting reactant. So we can conclude that we can produce at most 0.2793 moles of fluoride. Now we have to move on to the next part, so let me erase everything and come back. So looking over here, we see that the fluoride will be converted to calcium fluoride, which means that all of this will turn into this, which, kind of implies that we have an unlimited source of calcium that's precipitating the F- to produce calcium fluoride. So looking at this reaction, if all the fluoride becomes calcium fluoride, then we have to look at the mole-to-mole ratio. It's 2-to-1. So knowing that, we can multiply this by, for every 2 moles of fluoride, there's 1 mole of calcium fluoride. And notice how that's just dividing by 2, so this number divided by 2 is actually equal to 0.1397, or we could keep one more sig fig. We could say 0.13966. And notice how we have to keep 4 sig figs, so we underline the 4th digit. So we have this many moles of calcium fluoride. So the last step here is to find how many grams of calcium fluoride. So we have to find the molar mass of calcium fluoride, and according to the very beginning, we said the molar mass of calcium fluoride is 78.08. So we can multiply 0.13966 moles of calcium fluoride by the number, which is 78.08 grams per mole, and we get 10.90 grams of calcium fluoride, and that is our answer. Epsom salt or magnesium sulfate has, I don't know why that says has an unknown degree of hydration, which is the number of H2Os attached to the salt. A student decides to heat 10.000 grams of the hydrated salt several times until it becomes anhydrous. After drying off the salt, he weighs the anhydrous salt on a scale. The scale reads 4.883 grams. What is the degree of hydration for magnesium sulfate? So if you watched the Hydrate Lab video, you would immediately know how to do this, because honestly, it's identical to how that was done. So let's do this. So we have 10.00 grams of the hydrated form of magnesium sulfate. Magnesium is +2, sulfate is -2. So magnesium sulfate looks like that, and there's an unknown number of water molecules attached to the structure. And after the heating, 4.883 grams are left, and we're assuming that the leftover is the anhydrous form because after you heat it, all of the water is supposed to escape, theoretically. So the water that's lost is the difference between the two masses. So take a calculator, 10 minus 4.883, and here, let me change this since that's actually another 0, and we need to keep track of our sig figs. So we get an answer of 5.117 grams of water. Now let's do like a table to figure out the empirical formula. So this will be magnesium sulfate, this will be water, and we have 5.117 grams of water, and how much of the anhydrous? 4.883. Now we have to convert these to moles. So how do we accomplish this? Well, the molar mass of H2O is 18.02, and the molar mass of magnesium sulfate, well, I'm not too sure about that either. So let's look at this periodic table. Magnesium is right here, 24.31. Sulfate, well, sulfur is 32.06, and O4 is just 4 times 16.00. Add those up to get the molar mass of magnesium sulfate, so 24.31 plus 32.06 plus 4 times 16, and we get a molar mass of, I think, 120.37 grams per mole. And let's just convert these to moles now. So 4.883 divided by the molar mass of magnesium sulfate gives us 0.040566, no, it's actually 7, sorry. 0.040567 moles of magnesium sulfate. And we get for water 5.117 divided by 18.02. We get 0.2839, actually no, it's 2840 moles of H2O. So now we have to divide both of them by the smallest number. So it would be 0.040567 on both sides, and we get 1 mole of magnesium sulfate per about 7 moles of water. So we determine the ratio between the formula unit and the math waters, and it turns out the degree of hydration is 7. So this would be called magnesium sulfate heptahydrate. So magnesium sulfate heptahydrate. So now let's look at one last question. This one is an empirical formula one. It shouldn't be too bad. So let's do A. Calculate the moles of CO2 and H2O. Well, we have grams of H2O and grams of CO2. So just use the molar masses. This has molar mass of 18.02. This has molar mass of 44.01. So doing the math, we just do 0.279 grams of CO2 times the molar mass in the correct orientation. So it would be 44.01 grams on the bottom and a mole on the top. And doing the math, 0.279 divided by 44.01, we will get 0.00634 moles of CO2. Now let's do that for water. Now let's use blue for this. 0.172 grams of water times a mole of water has 18.02 grams, and we get a fantastic result of, well, I don't know, let's find out. 0.00954 moles of water. Note how there are 3 sig figs. So that's our answer for A. Not that bad. Now let's do B. Find the mass percentages of C, H, and N and the empirical formula for this compound. Now we need a new page for this, so let's go on to the next page. Let's write our moles of CO2 and H2O on the top. So it's 0.00634 moles of CO2 and 0.00954 moles of H2O. So they want the mass percentages for this compound containing C, H, and N. Now, how do we go about this? Well, we know that we have 0.125 grams of the compound containing C, H, and N. But we have nothing about N, but we can possibly find out how much C and H are in here. So how about this? Let's write a reaction, even though we don't have the full formulas for them yet. Let's just say the CHN compound reacts with oxygen gas to produce CO2 plus H2O. Now, where did the N go? Well, the N probably got combined with the O to form nitrogen oxide, so we won't focus on that. But what we will focus on is where the C and the H's went in the CHN compound. So the C all went to the C in CO2. So we can safely and boldly assume that all the carbon from the compound is in the carbon dioxide. So we can calculate the grams of carbon dioxide that are in the compound through here. So let's find the grams of C in CO2. So how do we go about this? Well, we know that for every 1 molecule of CO2, we have 1 atom of C. In other words, the number of C's is equal to the number of CO2s. So in other words, the moles of CO2 equals the moles of carbon. So knowing that, we can immediately pinpoint the moles of C. So we have 0.00634 moles of carbon. And let's find the moles of hydrogen. And we can know this because all the moles of hydrogen in the compound got transferred to the H2O. So we can boldly assume that all the H in H2O once belonged to the H in the CHN compound because the conservation of mass. So for every 1 mole of H2O, there are 2 moles of hydrogen atoms. So we just have to multiply 0.00954 by 2. So let me do that. By 2, we get 0.0191 moles of hydrogen. So we found the moles of carbon and the moles of hydrogen, all of which once belonged to this. We have to rely on what we absolutely know. We absolutely know that all our carbons and hydrogens from the CHN compound were all transferred to the C in CO2 and the H2 in H2O. So that's why we could pinpoint the number of moles of C and H in this compound, since the C's and O's, the C's and H's on this side must have all come from this compound and not this, because O2 doesn't have C or H. So let's find the grams of C and H, and we could probably figure out how many grams of N there are. So the molar mass of C is 12.01, so 0.00634 times 12.01, we get 0.0761 grams of carbon, and 0.0191 times 1.01, we get 0.0193 grams of hydrogen. Now, we can find the grams of nitrogen by subtracting the compound's mass, 0.125, by the mass of the C and the H to get the leftover N. So on a new slide, I will do that. 0.125 minus, let's see what the two numbers are, 0.0761 and 0.0193. So notice how this is C, H, and N, and this is C, and this is H, and we're left over with the N. Now, what is this? Well, 0.125 minus 0.0761 minus 0.0193, and we get that we have 0.0296. And notice how I'm going to underline this, since this had 3 decimal places, and that's the least of them. So this will be the tracker of, me having 2 sig figs for my answer with, 3 decimal places. So now we have the grams of nitrogen. Now we could create a table based on all this information. And later you'll see that the sig figs don't really matter in the end, but it's just good practice to practice doing sig figs whenever you can. So we have 0.0761 grams of carbon, 0.0193 grams of carbon, and 0.0296 grams of nitrogen. Now let's rate the question again. They want the mass percentages of C, H, and N. So how about this? Let's do the question in favor and do that first. So the total mass is, of course, 0.125, which is stated in the question over here. And let's just, do some division. So the percent composition of carbon is just the mass of the carbon, 0.0761 grams, divided by the total mass of the compound, 0.125 grams, and multiply by 100%. But I'm not going to write that, since to convert between percent and decimal, just move the decimal place 2 times. So 0.0761 divided by 0.125, I get 60.9%, and I'm staying true to sig figs. And what about our hydrogen? Well, 0.0193 grams divided by 0.125 grams, we get, 0.0193 divided by 0.125, we get 15.4% for, hydrogen, and this is carbon. Now let's do it for nitrogen. So nitrogen is just, let's see, where can I write this? Actually, I know, I could write it right under. So 0.0296 grams of nitrogen over 0.125 grams of the compound. So dividing these two and converting it to percent, we get 23.7% nitrogen. So these are our 3 mass percentages, and let's see if they add up to 100. 60.9 plus 15.4 plus 23.7, I get exactly 100%. So that's reassuring, because I know that these 3 mass percentages are right, and that's one way to check my work to see if all of them add up to 100. Now let's actually do the problem. So we have to convert these 3 to moles in order to find the molar ratio between the 3. So I have to divide this by 12.01, this by 1.01, and this by, 14.01. So those are the molar masses, and now let's find the moles of each. So doing the math, I get this many moles of carbon, this many moles of hydrogen, this many moles of nitrogen. I divided it by the smallest number of the 3, which is this one, and I got a 3 to 9 to 1 ratio. So our answer will be C3H9N, and that is the answer for the empirical formula, and that answers all the questions in the question. So they wanted the moles of CO2 and H2O, we gave them that. They want the mass percentages of carbon, hydrogen, and nitrogen, and the empirical formula. We also gave them that, and we gave them that. So that's the end of this video, and have a nice day.